FuelCell Energy manufactures, sells, installs, services power plants from 1.4 megawatts to 3.7 megawatts based on carbonate fuel cell technology. Technology that is now commercial, but that was in fact developed with a lot of Department of Energy support in the 1990s and early 2000s. We like to think of ourselves as being in the energy supply, recovery, and storage. Supply, of course, from power generation, a couple of recovery technologies, in addition to carbon capture, is recovering energy from natural gas pressure letdown stations using carbonate fuel cells, and also purification of dilute hydrogen streams using some of our other electrochemical technologies. And we're looking at using our solid oxide based fuel cells for things like hydrogen generation and hydrogen-based energy storage. But I'm going to focus on the carbonate fuel cells and their application in carbon capture today. A little bit more about the company. We are based in Danbury, Connecticut, about an hour northeast of New York, and about an hour northeast of Danbury, which is our corporate headquarters, is our factory in Torrington, Connecticut. So the fuel cell stack modules are built in Connecticut. And essentially exported. Our main markets are North America, Europe, and Asia, specifically South Korea. And I won't go through them all, but you can see this just shows a list of our customers behind the meter and in front of the meter, as well as strategic partners and investors. So a little bit about what fuel cells are, and then I'll show you how they can be used in CO2 capture. The picture all the way at the left shows a fellow who's actually holding a fuel cell. And a fuel cell is a thin sandwich. It's a fuel electrode that consumes fuel and makes electrons. It's an air electrode that consumes air and also consumes electrons. And you hook a wire between those two, that's power. And between them is a thin layer of electrolyte. And that electrolyte can be a variety of different things. In our case, it happens to be based on alkali carbonates, potassium carbonate, sodium carbonate, those kinds of things. So he's holding an individual fuel cell, and behind him there are 400 of them stacked up. So that individual thing he's holding makes a little less than a volt. So you've got about 350 volts or so in the stack behind him. And in our standard fuel cell package, we put 4 of those stacks inside an enclosure, and that's a 1.4 megawatt fuel cell module. That's what it nets after conversion from DC to AC and feeding parasitic load. We use one of those modules in our 1.4 megawatt system. 2 of them go into our 2.8 megawatt system, and we now have a 3.7 megawatt system that uses a third module. And that third module runs off leftover fuel from the first 2, so it achieves about 60% electrical efficiency. So it's like a natural gas combined cycle type efficiency, but at a distributed generation size. And it's targeted for a lot of the emerging non-CHP applications. Most of our units are deployed in combined heat and power applications. So that 3.7 megawatts is the biggest thing we make, but customers do bigger projects, and they do it by, as you see on the bottom there, just putting multiple units at a site. So this is a little bit of a view of what a typical 2.8 megawatt fuel cell power plant is. As I said, it has those 2 fuel cell stack modules. Each of them is netting 1.4, so it's 2.8 megawatts total. And the mechanical equipment, which you see in the middle of the system, which we call the MBOP, mechanical balance of plant, is just heat exchangers, air supply blowers, startup heater, that kind of thing. The electrical equipment, which we call the EBOP, electrical balance of plant, is DC to AC power conversion, because direct current is what comes out of a fuel cell. It's like a big battery, and switchgear and so forth for interface with the grid. So that's a complete system that takes pipeline quality natural gas or biogas and converts it to electricity. So I'm going to get a little bit into how it works because it's kind of important to explain how we can use it for carbon capture. As I said, all fuel cells, they're like batteries. And like in a battery, you have a chemical at one electrode that makes electrons and another chemical that consumes electrons and an electrolyte salt bridge between them that completes that circuit. In our case, that's a carbonate. So what happens at our fuel electrode is hydrocarbon fuel, typically methane, is converted to hydrogen, and that hydrogen is reacted to make electrons. Meanwhile, at the air electrode, air is being consumed, and it's consuming those electrons, and as I said, you hook a wire between them, and that's your power. What's unique about the carbonate fuel cell is that the ion transfer that completes that circuit is based on carbonate ions. And as a result of that, there's extra CO2 produced in our fuel electrode that needs to be recycled back to the air electrode where it's consumed. So for every molecule of methane we send in, a molecule of CO2 is going to go out the chimney. But And when you're in the fuel cell business, you can't use stack because it gets confusing. So a molecule will go out the chimney. But in addition to that one molecule of CO2, 4 extra CO2s are produced in the fuel electrode and recycled back to the air electrode where they're consumed. And the key to the high efficiency is this is an electrochemical process. You're not burning fuel to make electricity mechanically. You're avoiding some of the emissions from high temperature combustion. But the key for carbon capture is that little CO2 recycle, which is pretty inconsequential for power generation. But what we realized as we started to do this work is that if you interrupted that cycle, if you took most of the 4 CO2s that are coming out of that fuel electrode, you would need to provide some other CO2 from some other source to the air electrode because it needs them for its reaction. And that source could be the flue gas from a coal power plant or some other combustion source. So the idea is that you could literally use this fuel cell for carbon capture. And as we got into the work, and DOE has been supporting this work for a few years right now, as we got into the work, we found another benefit, which is that if you send a flue gas with NOx into our air intake, as that NOx flows through our air electrodes, for a variety of mechanisms that it took us a while to figure out, about 70% of that NOx will be just destroyed, just flowing over the air electrode catalytic surfaces. So that's a nice side benefit. Plus, as you see, in addition to all those CO2s, there's 4 waters that are produced at the fuel electrode, and so it's a net water producer, this system, and that's an additional benefit in a lot of areas. So the application for carbon capture is kind of shown schematically here. You basically take our standard fuel cell stack module and you add some stuff to the balance of plant that allows you to extract the CO2 that's coming out of the anode. And the key is that you're trying to capture CO2 from a pretty dilute source. Depending on the fuel, something like 5 to 15% CO2. It's hard to capture and purify. But when you flow that into our air electrodes, it gets electrochemically pumped from that dilute stream to a much, much smaller stream, our fuel stream. So when it comes out of our fuel electrodes, that fuel exhaust gas is it's leftover fuel. It's about 70% CO2, and the rest is mostly hydrogen. It's very easy to separate the CO2 from that stream. So essentially, the fuel cell, while it's making electricity, is acting as an electrochemical pump for the CO2. And it's that co-production of electricity while you're doing carbon capture that enhances the economics, because instead of taking a 500 megawatt coal plant and adding a carbon capture system on it that converts it to a 300 megawatt coal plant, you're taking a 500 megawatt coal plant and you're adding 300 megawatts of power generation to it. So it's a whole different type of economics. So the applications are pretty much what you'd think. Capture from large-scale coal systems, capture from natural gas plants, capture from industrial processes, boilers and so forth. And one interesting application is capture for enhanced oil recovery, because you can think in terms of having systems that are actually at the oil production site running off associated gas producing CO2 that can be used for enhanced oil recovery on site. So a little bit interesting sort of distributed CO2 production for EOR approach. So as I said, Department of Energy has been funding the R&D for a few years now. We have done small cell testing to identify exactly what impurities do to the fuel cell, the types of impurities that you would see in a coal plant. We have done stack testing, so-called bench scale testing, and now we're moving on to doing the first megawatt scale demonstration. And this is going to be at a coal plant at the James M. Berry electric power generation plant right outside of Mobile, Alabama. It's an Alabama Power Southern Company plant. And there's about 2 gigawatts of generation there, roughly half and half coal and natural gas. We are going to connect to the coal exhaust and take a slipstream, of course, because we're just going to be one 2.8 megawatt plant. We're going to capture 90% of the CO2 from a stream that's equivalent to about 3 megawatts worth of coal generation. And it's going to be the first megawatt scale demonstration of this technology, so we're pretty excited about it. And so the DOE program has been focused strictly on coal, and in parallel, we've started a development effort with ExxonMobil to look at capture from natural gas sources. There are some differences. It's a lower CO2 level, probably a hotter exhaust, and it's possible that after we do the DOE demonstration on coal, it's conceivable we could use that same pilot for demonstrating the natural gas technology we're developing with ExxonMobil, but they're 2 separate programs, basically. And so, as I said, it'll use one of those 2.8 megawatt systems that I show you. We have to modify the BOP to add equipment to extract the CO2 from our anode exhaust and pressurize it and liquefy it. And that's what we'll be basically doing at that site. So that's a stepping stone to what we all see as the ultimate goal, which is large-scale systems that are capturing lots of CO2 from very large-scale coal plants. So this is a picture of the system that we've been designing under the DOE program. It's a 350 megawatt system that will capture 90% of the CO2 from a 550 megawatt coal plant, which is kind of the base design plant that we're using in the program. And I showed you the 4-stack module that our current products use to achieve this kind of scale. It's more economical to look at very large multi-stack modules. So these stack modules have hundreds of stacks in them instead of just 4 to make it more compact. And so because of the low cost of fuel cell equipment and the fact that you're generating a revenue stream of power, the cost analysis that we've done and that we continue to do indicate that we're on track to meeting and doing better than the DOE targets of $40 a ton or 2 cents per kilowatt hour cost addition. So again, it's the co-production of power that makes this an attractive way to do carbon capture. So this is where we think the technology and the application goes. This is the home run. This is what we're working for. But what we've asked ourselves is, in the meantime, as we're developing this technology, are there near-term applications that we can use kind of to help us get down the road with this technology? And so one of the things we've thought about is that, well, what if you took one of those 2.8 megawatt plants and modified it for carbon capture and actually put multiples of those, the way some of our customers do, what we call fuel cell parks. And you could start to think about doing either carbon capture from a smaller system, from a thermal system, or incremental carbon capture from a larger system. This happens to show 12 of those units that would be capturing 500 tons a day from a coal flue. Plus it captures its own natural gas fuel. These are fueled by natural gas, so we have to capture 90% of the CO2 that's in the coal flue, plus 100% of the CO2 that we're introducing from the natural gas. So this system, for example, would produce 700 tons per day of CO2. And that's probably too little to think about sequestering. It's definitely too little, unless there's an actual ongoing well. But it's not a bad quantity of CO2 to think about for finding an industrial CO2 off-taker, like an industrial gas company or a specific user. So this could be one way that we start to get this technology out into the marketplace as we move forward toward that very large-scale vision. So finally, just to wrap up, this is a really interesting technology primarily because of that co-production. It utilizes this commercially available fuel cell technology with modifications to the balance of plant systems. So it's the electrochemistry is exactly the same in carbon capture as is in operation in hundreds of power plants around the world. It's modular, lower cost, primarily from the co-production of power. I mentioned the NOx destruction as an additional benefit, water production, and I can't stress this is invented in the U.S. without a DOE support, manufactured in the U.S., and it's great to see. We got some DOE support for the core technology, commercialized that. That was a real success story, we think, and we think we're on track for another success story with the same level of support in this new step in the technology.